Swayam Prabha. Digital India. Educated India.
Let us look at a very simple application of this Bernoulli's equation. Okay. You will have many such examples in fluid mechanics book. We will just discuss one of them, okay, and all others many will be representative of this. Some terms will be given, some terms will be asked to find out. Okay. What is that we are interested in? Remember, the next level of application is going to be finding velocity profiles. Okay. That is, we are going to predict velocity profile. For example, in our flow between the parallel plates, we are going to predict the velocity profile where one plate is set in motion, and then when both the plates are fixed, we are going to predict the velocity profile to be parabolic, etc. Okay. Now, suppose you want to measure the velocity profile in between the plates or in a pipe, how do you measure? Okay. And that is the arrangement shown here. This arrangement is used to find out velocity at different points in a pipe. When I say different points, along the diameter, okay, or between or along the if you have two plates, you are interested if you have two plates, you are interested in finding out what is the velocity here, 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 etc. Okay. Okay, not just the average velocity. Okay. Okay, now, what is the arrangement? What is shown here is a pipe carrying water, and then you insert make a hole and then insert a tube in this way on the wall of the pipe. Now, water rises based on the static pressure at that particular location, and that static pressure is balanced by the level to which water rises here. So, you make a hole and attach a small tube, water will rise, and that will represent the static pressure at that particular point, and the static pressure is represented by the height to which the water level rises. Now, you make another tube of this shape, L shape. Why L shape? This end should face the flow, okay. And once again water rises in this tube as well. What happens now? Let us say water has some velocity at point 1, and when it reaches point 2, it gets decelerated, the velocity becomes 0 at point 2. So, it loses out all the kinetic energy, and so that results in a increased pressure, and that is why you observe a higher level here. That increased pressure is represented by the water level in this tube. So, the first tube represents the static pressure, the second tube reflects the increased pressure because of the conversion of kinetic energy. Now, let us read the example question. A piezometer, when I say piezometer, this simple tube is called a piezometer, and a pitot tube, this is a pitot tube, are tapped into a horizontal water pipe, okay, as shown in figure to measure static and stagnation pressure. What the piezometer measures is a static pressure, and the second pressure is called the stagnation pressure. This bracket you will understand in the next slide. Okay. Okay. And why is it stagnation pressure? Because the velocity becomes 0 at that particular point. Okay. For the indicated water column heights, what are the water column heights indicated? This is 3 centimeter, and this is 7 centimeter, and then 12 centimeter. Okay. So, here the water rises to 7 centimeter, here the water rises to 7 plus 12 19 centimeter. Of course, you have a 3 centimeter between the point, in this case we are interested in measuring the velocity along the central line. So, the point of measurement and the wall, there is a 3 centimeter height. Okay. So, now let us write the Bernoulli's equation. which says that P by rho plus V squared by 2 plus G z is equal to constant along a streamline. Now, what we will do is we will choose a streamline along the center line of the pipe, and point 1 is directly under the piezometer, okay, and point 2 is at the tip of the pitot tube, okay, that is what is shown here. One is just below the point 1 is below the piezometer, 2 is at the tip of the pitot tube. Okay. Now, because points 1 and 2 are along the streamline, this sum should be same at point 1 and point 2, and that is what is written here. The same sum with subscript 1 for point 1 and the same sum of terms with subscript 2 for point 2. This should be same because we are considering points along a streamline, and that is what we have discussed. The sum of these 3 terms should be same. Okay. Now, points 1 and 2 are at the same level, they are all both the points are at the along the center line of the pipe, and then this we have already discussed. Stagnation point 2 is a stagnation point, and we have just now discussed stagnation pressure is obtained when a flowing fluid is decelerated to 0 speed, that is what we discussed. Whatever velocity here it loses, it decelerates and becomes 0 velocity at the tip of the pitot tube. Okay. Now, okay, let us write down the Bernoulli's equation, which means the sum of energy at the 2 points are same, and because the levels are same, so Z1 and Z2 are same. Z is the level from some datum, some reference, and we have seen the stagnation point, the velocity is 0, which means that V2 is 0. Okay. So, that is a simplification which we are going to apply for the Bernoulli's equation. Okay. So, which means that the left hand side you have P1 by rho plus V1 squared by 2, and the right hand side we have P2 by rho. Okay. Now, this P2 is called the stagnation pressure. If you take rho to the left hand side, what do you have? You have P1 plus rho V1 squared by 2 is equal to P2, and that is why the question it said the P2, the stagnation pressure, is equal to the static pressure, and this term is called the dynamic pressure. So, the stagnation pressure represents the sum of static pressure and the dynamic pressure. Okay. Okay. And that is why you have a higher level of rise of water in this particular pitot tube, okay, compared to the piezometer. Okay. What is it we are interested in? We are interested in finding out the velocity, which is in the dynamic pressure term. Okay. So, the dynamic pressure is the difference between the stagnation pressure and the static pressure. Okay. So, rearrange this equation for velocity. P1 is equal to root of 2 into P2 minus P1 by rho. Remember, the difference between the two pressures represents the dynamic pressure. Okay. P2 is stagnation pressure, P1 is static pressure. So, now let us evaluate what is the pressure at point P2, and that is represented, the pressure at point P2 is balanced by the hydrostatic head of liquid in the pitot tube. And what is the hydrostatic head? This H1 plus H2 plus H3 into rho, of course into G. And what about the static pressure? The static pressure here is balanced by the hydrostatic head of water in the piezometer, and what is that? H1 plus H2 into rho into G. And what we are interested, or what is it required, is P2 minus P1, of course H1 H2 cancels out, leaving us with H3 into rho g. Okay. Now, let us substitute that for P2 minus P1 as H3 rho g, rho cancels out, we have root of 2 g H3. So, only the difference in the liquid level between the piezometer and the pitot tube matters, okay, because only H3 plays a role in the final expression for velocity. So, H3 is 0.12. So, if you substitute, you get 1.53 meters per second. Okay. And what we usually do is, because it depends on the level difference, we connect a U tube manometer here, okay, we connect a U tube manometer here and directly measure the pressure difference. We need not measure separately the static pressure and then the stagnation pressure, just connect a U tube manometer, that will give us the pressure difference, and that is what is written here. Velocity depends on pressure difference measured by connecting a manometer. Okay. And remember, the velocity is high. Remember, we should be at high velocity because we are considering the flow to be inviscid, and we are also in this case quite away from the wall, and we said inviscid flow prevails in the region away from the wall where net viscous forces are negligible. Okay. So, that condition is also satisfied. Okay. As I told you, this method is used to measure the radial profile of velocity in a pipe, or it could be even velocity between the two plates. Okay.